eval back. What's the name?
Huh?
What's the name?
Tom.
Yes, sir. So, again, game plan for today then is let's get through chapter 3, and then we'll worry about the other stuff as it comes along. There's a whole bunch of problems that I think were provided along with that document that I put on Blackboard, the free body diagrams document. Whether I did or didn't, I'm not 100% sure, but I think I did. And I want to walk through several of those because what these problems here do, and really what the rest of chapter 3 is going to do for us, folks, is just give us some insight into, okay, how do we do basic equilibrium problems? If you think about the tools we're building into our toolbox right now, you know, we know how to make free body diagrams, and we know that's a skill set that for a lot of us, you know, we're going to continue building that and just, you know, perfecting that process over time. I think we've all bought into, let's put it this way, we better have all bought into the idea that everything hinges on the free body diagram being right. If you're the opinion is like, I can make them sort of right and I'm good to go, you are sort of, no, you're not sort of, you're completely wrong. You can't do it that way. They got to be right. So let's make sure, even with the evals that you got back, folks, if you didn't, you know, if you got some things marked off on that, you got to make sure that you understand, well, what did I miss? And as far as that evals thing goes, the free body diagrams portion of that, most everybody did really, really, really good on that, which is exactly what I want to see. Some of the common mistakes, the most common mistake was that inclined surface was a rough surface. So because it was rough, there has to be a force along that surface as well. We should have had a normal force and a force like this going parallel to that surface. So a lot of folks missed that. A number of folks did not include the coordinate axis system. And I know I've been clear as a bell that has to be there, otherwise it's not right, simple foot. A number of folks had that. Otherwise, it just really wasn't much wrong. So that's all really good. So, all right, done with that now. Let's take a look at a problem here, folks. Give me a moment to draw this problem. And before we even attack the problem, we're going to talk about strategy. So let me get this thing drawn up here. It'll take a moment, like I said. In this, what horizontal force P must a worker exert on the rope to position the 50-kilogram crate directly over the trailer? So let's stop right there. I heard a couple of important words. Horizontal force. Why do you think they included the word horizontal? Like, who cares otherwise? What do you think?
That way you know it's directly aligned with the parallel to the x-axis.
Exactly right. If we use a standard x and y coordinate axis system, that's signaling you that there's no angle on this. It's going to be a purely x-directional force. So we got that part. We know the worker is exerting this on the what? The rope. So therefore, that can only be a tension member. We got that part down. And then we're told that it's a 50-kilogram crate. And folks, I think I've said this before, when you're working these problems, even before you start thinking anything, if you see something in the narrative that is like, that's not a standard unit, like in this case here, 50 kilograms, that's not a force, that's not a weight, that's a mass, right? If you see something like that, man, before you even start thinking about working that problem, fix that. Get that little bit out of the way so we don't have to deal with it. So in this case here, 50 kilograms, we're going to multiply that by 9.81 meters per second, which is going to make that 50 kilograms convert over to 490 and a half. So 50 kilograms times 9.81 meters per second squared. That's going to be 490.5 newtons. So we know right now, before we even do anything with this, that this crate is weighing 490 and a half newtons. So we want to figure out what's the force we need to exert on this rope to position this crate directly over the trailer. We know there's a little offset right there, and the worker's pulling it over like so. Now, the dimensions given here, the dimensions we've got to work with right here. Something that is not said in the narrative, but I think it's important to know, is that we got no reason to think that the weight of the crate is anything but uniformly distributed, meaning that it's not like it's 490 pounds, like there's a 490 pound block of lead over in this corner here and nothing over here that would cause the crate to tip. Why is that important to us? Well, it tells us that we can reasonably assume that the weight would be passing through the geometric center of the crate and therefore aligned with this cable right here. Now that's probably one of those that's just intuitive, but it's worth saying, I guess. So folks, now we've got the narrative, we got the graphic, and let me ask you this question. At this point, everything we've talked about so far in the course, our process would be to now pick something to draw a free body diagram out of. What you thinking?
But before we get to that, I didn't quite get the full narrative breaking down. I just want to make sure I
Gotcha.
have everything before we get
Gotcha. So, and thank you for the question. So the idea here is we've got a worker over here. Crate is offset, as you can see, from the center of the trailer down here. It's meant to represent a trailer, offset by about 1 meter here. The idea is we want to know how much force does the worker pull to move that crate over so it's centered directly above the trailer. That's the question. So, our steps that we talked about so far are understand the narrative. If we don't have a graphic, make a graphic. Then onto a free body diagram. And then from the free body diagram or free body diagrams, there's always a possibility we might need more than one, right? From that, we derive our equation to solve the problem. Now, this is a loaded question. And it's kind of we can go down one path or we can go down another path. In one path of the question I'm about to ask you, if you right now were asked, what would you make a free body diagram out of to solve this problem, what would anybody suggest? And remember, we can make a free body diagram out of anything we want. But before anybody answers that, is there anybody in the room that would say, this graphic is no good? So, thoughts, anybody? If you just want to say, hey, I'm going to free body diagram of this and see what I get, what do you think?
So since the horizontal, the rope that's moving is what, 1 meter above the crate itself.
Yeah, a couple meters, yeah.
I feel like getting a free body diagram of that prior to going to the crate itself is probably going to be pretty important because that's where all the force is being applied.
Yep, absolutely fair point. Absolutely fair point. And again, this goes to the narrative we talked about before, that you can always pick a free body diagram of something. It may yield fruit, it may not. The free body diagram that we just talked about may do something for us, it may not, we don't know. But there's no wrong answer on that, so yes, fair. What other thoughts? Does somebody see something on this diagram right now that you're looking at that thinking, if I made a free body diagram of that, I get the solution I'm looking for? Now remember, free body diagrams, in order for us to get our solution, we have to have at least one free body diagram that shows a known force and also shows the force you're looking for. Or there's still pathway B where it's like, this diagram's no good. Now you guys already know diagram's no good, so I wouldn't be talking about it if it wasn't the case. But it's okay, we don't need to see that just yet. We don't need to see that just yet. Or if you see it, tell me what you see. Tell me why you think it's no good. But we've got one idea and a good idea for a free body diagram. What other ideas might somebody have? What you thinking?
Suspended from a cable, the limit rotate as it goes. Don't necessarily know like how much.
Do you mean like, so it's suspended from a cable like this, do you mean rotate along the axis of the cable, or do you mean be pulled over?
But the angle would change from the
Yes, you're 100% right on that. You're seeing the problem with this image, okay? And we're going to come back to that. Let me throw one at you guys. We said we can do a free body diagram of literally anything, right? If we can draw a free body diagram of literally anything, is there any reason I can't draw a free body diagram of that knot right there, or whatever that is, whatever that connection point is? The answer is obvious. If I can do a free body diagram of anything, then yepers, go right ahead. So, all right, let's say that I did a free body diagram of that knot. That's all I care about is just the knot. So I do the hardcore artwork for that. I include my coordinate axis system because, as we've already talked about, that's going to be important. And now, coming off of that, I think about, okay, a free body diagram means I've drawn a representation of the thing that I'm doing the free body diagram of. Now I'm going to include its weight. We know nothing about the weight of the rope or the weight of the knot, so not worried about that. And then we just kind of go around the horn and say, okay, we've got forces wherever I used to be connected to something, wherever I used to be in contact with something. So this knot right here sure used to be in contact with a cable right there, and we know from cables, we've already talked about this from cables, there are always tension forces. The line of action of the force goes along the line of action of the cable, and because it's a tension force, that means the arrow from the free body diagram must be drawn away from that. So I might have this here, and let's call this one TC upper. How about that? How about T? I'm just going to call it T upper, meaning the upper cable. So the tension in the upper cable. And that knot used to be in contact with the tension of the rope that the worker's pulling on. Now the narrative referred to that, that pulling force as force P. So in that case, the tension in the rope must be the force P that we're looking for. And then lastly, folks, we've got the knot used to be in contact with that cable right there. So we got a force going down here. Now, it should be clear to everybody that the force in this cable here has got to be the weight of this, of the crate. If we don't see that, then it's easy. Just do a free body diagram of the crate, and you're going to find out that the tension of the cable has got to be the same as the weight of the crate. So we already know that that's 490.5 newtons. Now, that right there, folks, would be a complete free body diagram for the knot. And again, we can do a free body of anything, so it's a perfectly legit free body diagram, right? So now, without even writing on the board, let's sum forces in the y direction. Folks, sum forces in the y direction, don't even write it down. Tell me, what is the value of T upper? 490.5. I think you said negative, it would work out. Yeah. But 490.5. I hope everybody saw it. My hope was that everybody was going to, in 30-some part harmony, or whatever the number is, would yell out 490.5. If I sum forces in the y direction, 490.5. Done. All right, now let's have some harmony on this one. What's the value of P if we sum forces in the x direction? You're all seeing it. What do you think? It's not negative P. No, that's good. But so we're just summing forces in the x direction, right? P is a purely y directional force, so nothing there. Summing forces in the x direction. You just think of the equation. I'd have minus P, to your point, equals what? 0, exactly. So using this free body diagram right here claims that the worker wouldn't need to apply any force to the rope. The crate's going to magically work its way over to above the trailer. Why is that utter? Well, that's a moot point. That's a rhetorical question. I was going to say, why is that utter nonsense? Well, because we know it's not going to magically go over there by itself, right? But we already had insight as to what the problem is. The problem here, folks, is this. The diagram is showing a static state that doesn't represent what the narrative is saying. The narrative is saying the worker's pulling the crate over to above the trailer. This diagram shows the steady state with the crate offset from the trailer. So the problem here was our graphic. We haven't seen this before. We've not run into one of these yet. It's like every time the authors give us a problem, we read the narrative, and we look at the picture, and it's like, the picture is exactly what we're talking about. And all of a sudden, here comes this. Thank you, authors, right? So now we see what we have to do to fix this is we actually need to draw this in a little bit of a different way. We need to represent what the narrative is talking about, where we've got the cable pulled over, we've still got the knot here, we got the crate hanging above the trailer here, but now it's centered over the trailer. I'm sketching this really fast, folks, because we don't need to get into details. We still got the worker pulling on this, so here's the worker doing the worker's thing, right? Pulling on that. But that diagram right there represents the state that the narrative is talking about. Okay, so now with this, let's take a look at some things. First of all, before we even think about a free body diagram, now realize, and this, boy, you've heard me say this a few times this semester, haven't you? We look for triangles, right? So in this case here, I see a triangle right here. Scale might be a little off, but I see a triangle here where I know that I had to pull this over this distance right here. So this is 1 meter here. And I know the length of this rope right here. The length of the rope from the knot from here to here was 4 meters, which means the hypotenuse of this triangle here, the hypotenuse is 4 meters. A common mistake that folks will make is you pull this over and you think, well, this length here was 4 meters because that's what this showed over here. I didn't finish up this very well, did I? But that's what this showed over here. It was like 4 meters high. But no, the 4 meters in this case was the length of the rope. So that right there, folks, that is the thing that we need to solve. That's represented, 2 seconds, I'm going to come right to you. That's representative of what the narrative is talking about. How much force does the worker have to pull to get this situation, not that situation? Junior, go right ahead.
Why is it now 2 meters instead of 1 meter? Why'd you put 2 instead of, why you put 1 instead of 2?
Oh, good point. Yeah, well, no, it's because it's that way. So the 2 meters here was representative of how far from the knot down to the center of this. So here to here is still 2 meters.
Mm-hmm.
What the 1 meter represents is, if you look at here, we've moved it over so that the center is over, the center of this is over here now. That distance right there is that 1 meter right there. So that's why I got the 1 meter in that dimension.
Okay.
Great question. Good question. What you thinking?
So it's 4, not because it's C equal, you're not doing the Pythagorean, it's just sort of the same thing.
Exactly. What I'm looking at here, is, again, very, very good question, is, okay, the length of this rope from this knot to that point right there is 4 meters.
Yes.
So if I slide this up here, it's still 4 meters. Yeah, right away.
Does it factor in that when you tug on it, that is giving a very slight angle to the rope?
Fantastic question. The point that you're asking here, and I heard the question, and I may be giving you 2 answers. I think what you're suggesting is when you tug this over, is there a little bit of this in the rope, a parabolic sense?
The rope that's being pulled, well, yeah, I recognize that. The rope that's being pulled, though, is slightly angled.
Yeah, you're 100% right. That's a great point. Here's where we have to go back to the narrative, and there's 2 ways to look at this. The narrative said what horizontal force, right?
Yeah.
So we assume that the rope stays horizontal. The other is we weren't given any information, so even if it was on a bit of an angle, we wouldn't know what it is, so we don't have any ability to, we wouldn't have any ability to analyze that. That's a great question.
Because the other way my brain was thinking about it was if he was pulling on like some sort of sliding part that's not actually fixed to the rope, then the length of the 4 meters would increase slightly.
This is true, and that's also true in the sense that this is a non-rigid member, so therefore, right? Yeah, we just don't have any of that info, though. So all your questions are great, but it's the danger of trying to read a little too much into this right here. But yeah, I love your questions. They're good. What other questions you guys got? Love these questions. They're always good. Okay, now let's go back. First of all, before we go any further, let's figure out what this angle is right here. We know we're going to need an angle. So as I look at that, I realize I got a 90-degree angle right here. So I'm seeing, with respect to this angle, I'm seeing that I have a adjacent leg. I see that I have a hypotenuse here. So this angle here, which I'll just temporarily call theta here, the cosine of my angle theta, therefore, again, remember cosine is adjacent leg over the hypotenuse, nothing new there. That's going to be what? Adjacent's 1. Hypotenuse is 4, so that means theta inverse cosine of 0.25. That's going to be 70, whatever it is, 75.52 degrees. Okay, so now we got that. Now, folks, with that said, Now let's go back to our strategy. We're still gonna make a free body diagram of the knot. There's no reason to change that. We just wanna make that free body diagram representative of what's really going on here. So now if I do that free body of the knot, like so, I now have my tension in my upper cable going off like this. So here's my T upper, as we had before. I've got that 75.52 degree angle right there. No, I'm not going to forget my X and Y axis system, although I had it written down over there anyway. I've got the force P that I'm pulling on horizontally here, and then we've got the weight force here, 490 whatever I said it was, 490.5 newtons. And now we've got a free body diagram, folks, that at this point I would encourage us to solve it. So we got a free body diagram. Let's remember we're looking for P right here. So let's sum forces in the X direction. So if we sum forces in X, remembering that per our coordinate axis system, positive X is that away, right? So I'm going to have the X component of the upper, of T upper right here. So the X component of that is going to be tending towards the positive X direction. So the X component in this case is going to be T upper times the cosine of that angle right there, which ironically we already know the cosine of that angle is 1/4. So so that's going to be, I'll write it out anyway. So T upper times cosine of 75.52, which again we already know is going to be 0.25 or 1/4. And then the 490.5 that we see right here is purely Y force, so that's not going to show up in that equation. But P, that's a purely X directional force, and it's going in the negative X direction. Positive's that way, so we drew that one in the negative direction, so minus P, and that's going to be equal to 0. And of course, if we step back and look at that, we realize that in that one equation we got two unknowns, so therefore we can't solve it, so no problem. Let's go ahead and solve sum forces now in the Y direction. So if we sum forces in the Y direction, here's the great news on this equation. Since P is a purely X directional force, it's not going to show up in this equation. But we're going to have, in this case now, if we resolve this into its Y component, the Y component for T upper is going to be trending upwards. So it's going to be positive, so it's going to be T upper times, in this case, the sine of 75.52. Minus 490.5, because that's trending downwards in the negative Y direction according to our diagram here. So minus 490.5. And we've already said that P is not in that equation, so this has to add up then to 0. Which means now that T upper, we can solve this equation for T upper if we, oh, I did that really poorly. Hang tight here, folks. I want to make sure I got this right for you. That's equal to 0. Let's not confuse that. But I can solve that equation right there for T upper. So according to this equation right here, T upper would therefore be equal to, if I bring this one here to the other side, equal sign is going to become a positive, so it's going to be 490.5 divided by the sine of 75.52. And folks, if you plug that in, you crank that out, you are going to find that that value ends up being about 506.6 newtons. So 506.6 newtons here. And now that we know what the value of T upper is, we can come back and substitute it right there. So according to this equation, which I'll bring down here, if we bring P over to the other side, the equal sign is going to become positive. So we're going to have P is equal to this. So T upper times, we've already said 0.25. But we've already figured out that T upper is 506.6. And if we take 1/4 of that, we're going to end up with right around the final value here of P being equal to about 126.7 newtons. And that right there, folks, solves the problem. I didn't talk about this much before we started this, but you know, I have talked about in the past that I really, really like it when we ask ourselves before we even start working on a problem, like, what do we expect, right? What do we think it's going to be? And in this case here, if you just go back and think about this, you've got a crate hanging here that's 490 newtons. That's the weight of the crate hanging there. Now folks, think about this. If you had a rope in front of you right now, something hanging from that rope, and you pull that thing over a little bit, I think all of us would agree that common sense tells us that we're not going to pull nearly as much as the actual weight of whatever that thing is to get it to move over, right? That's just, our experience should tell us that. So right off the bat, we should have been thinking that whatever this number is here, it's going to be somewhere less than that. Was it a lot less than that? Was it a decent fraction of that? We don't really know that. The answer came out though at 126.7, so therefore what, about a quarter of it roughly, right? A quarter of that, and that just kind of, that resonates from a common sense standpoint. Now think about this. If you had a crate hanging there and the crate really weighed 490 newtons, and you got to pull a rope to get the crate to just slide or swing over just a little bit, and your math comes out and tells you that you need like, what, 5,000 newtons or something to do that, that should bother you, because if that's the case, it'd be easier to just go pick up a crate and hold it over the wagon, and it'd take less work to do that. So that would tell us, hey, if I got a big number like that, something went wrong. But okay, let's talk takeaways. The takeaways here were that, in this case, number one, it only took one free body diagram to solve this problem. In fact, here in chapter 3, most if not all the problems we're going to run into in chapter 3 need a grand total of one free body diagram. Chapter 4 is where we transition out of that and say, okay, now we got more complex things. We're going to need multiple free body diagrams to solve this. But here in chapter 3, it took a grand total of 1. The big takeaway that I want you to have here is that it would not at all have been wrong in any way to make a first free body diagram of that knot the way we had it before we realized, oh, we're going to pull this knot over, we're going to show this on an angle versus straight and down. It would not have been wrong in any way to do that and to not get any yield out of that, to get no fruit out of that. And all that does is that says, okay, I'm missing something, all right? Let's stop and let's figure out what we're missing. In this case, we saw that if we left the rope straight up and down, then our finding for the value of P is going to be 0. And again, we knew it's like, okay, no, that's not right. So we used that to figure out what did we miss. What we missed was the diagram, in this case, a rarity, by the way, folks. We're not going to see much of this, but a rarity where the diagram we're given is purposely wrong. We had to fix the diagram. We had to make the diagram match the narrative. And then after that, one free body diagram, we get the free body diagram right, then the equations of equilibrium, done, we're out of this. That's the takeaway. Is that by the time we get to the right free body diagram, the rest of this is just, it's automatic almost. Any questions on that one, anybody? Fantastic. Okay, let me clean that up. We'll move on to the next. We're going to do a grand total, I think, of 4 problems today. And I've already tipped my hand that in all these problems where you should anticipate that we're going to solve each one with a grand total of just one free body diagram. This next one here, folks, let me draw it first, then we'll talk about it. This one here has got some weirdness to it. Okay, so I've started with the diagram on this one, and this is, again, this one's a narrative that we need to work through meticulously. We're putting the engineer's detail on this. Let's look through the narrative here, and I'm going to go through this piece by piece. The very first 2 or 3 words of the narrative goes like this: the 20 kilogram uniform rectangular plate. If I'm you, I stop right there. I just saw kilogram. I couldn't care less about what the rest of this reads, but I saw kilogram, and I know that I got to convert that up to its equivalence in terms of weight. So in this case here, my weight is going to be, what do we say, 20 kilograms? So 20 kilograms times 9.81 meters per second squared. And folks, that's going to be equal to what? It's, I actually don't know if I even wrote it down in my notes. I think I just wrote it through that way in the equation, but it wouldn't hurt us to get that part figured out. So 20 times 9.81, 20 minus 0.38, so 62, yeah, thank you, 19.62. So 19.62 newtons on that. Now let's continue on. So now we could read this as not the 20 kilogram plate, but the 19.62 Newton. And hear the word here, folks, uniform rectangular plate. Yeah, fire away.
Shouldn't it be 196.2?
Oh, probably. Yeah, 196.2. Thanks. Yep. Thank you again. The dangers of mental math, right? So, okay, now the 196.2 uniform rectangular plate is supported by an ideal pivot at O. Man, there's a lot buried in this one. So we just saw the word uniform telling us that this plate, even though you could argue that, well, it's not exactly uniform because there's a pinhole in the plate here, so it can't be perfectly uniform, which is true, but they're telling us it is, so just treat it that way. So what they're saying is, since this plate is uniform, that 196.2 newtons of weight is going to be applied right through the geometric center of this. And by the way, well, let's all say this, where does weights point to? Straight down towards the center of the earth. So we know where that weight's going to be on that one. So we got that, and then hear these words again. Is supported by, quote, an ideal pivot. What's that word ideal telling us? We're talking about the pivot. Yeah, what you thinking? Exactly. So up here at point O, this so-called ideal pivot can also be read as frictionless, smooth. We use these words kind of interchangeably throughout here. So we got an ideal pivot at O and a spring which must be compressed prior to being slipped into place at point A. So what we're saying here is there is a spring that has an original length on it right here, and in order for that spring to support this plate, it has to be compressed before it gets put in under here at point A. So spring must be compressed prior to being slipped into place at point A. If the modulus of the spring is K is equal to 2 kilonewtons per meter, let's write that down. The modulus of the spring K is equal to, again, 2 kilonewtons per meter. We're going to come back and talk about that in a second. Here's the question posed to us, folks. What must be this spring's undeformed length? In other words, what was the original length of the spring, which had to be compressed down to a height here of 0.1? What was the original length of that spring before it got compressed down? Like I said, this one is a weird problem. I mean, this is not one that's just one of those like straightforward, like, hey, what's the force here? This one takes us in different places, but let's get to what right now seems odd. We're gonna see how quickly we're gonna turn this into something straightforward. It all goes to the spring and this thing called the modulus. So folks, modulus of a spring is also known as the spring's stiffness coefficient. All springs have a certain stiffness coefficient which tells us it governs how much force it takes to compress or extend the spring. So think about this. If I went to a hardware store right now and I bought a little compression spring that's maybe big around as my finger, I probably can take that compression spring and apply some force and squeeze it, right? Let's go and take the compression springs out of the suspension of our cars, which are also compression springs, but about this big, and try to squeeze that together. Clearly, it's going to take a lot more force to squeeze the automotive compression spring than the little one I just bought at Ace Hardware, right? Difference? The difference is one has a much higher spring stiffness or spring modulus, right, than the other. In this case here, we're told that this spring, whatever it is, has a modulus that it takes 2 kilonewtons of force to compress that spring 1 meter. What that means for us, though, folks, is this. Think about any spring you've ever run into, whether it's a compression spring or whether it's a tension spring. We all know that if you compress a compression spring, it's going to push back on you with a certain amount of force, right? It takes a certain amount of force to compress it. Old man Newton says it's going to take an equal and opposite amount to push it away. The force in that spring, for a compression spring, the force in a spring is equal to the modulus times the deformation of the spring. So that K value over there times how much did the spring deform. That tells us what the force of the spring would be. Now, we're going to see a problem right after this one in which we're going to do the exact same thing with a tension spring. And I'm going to show you there where the authors actually kind of lied to you a little bit about how we're going to manage that, but let's save that for a little bit later. So right now, the force of the spring is nothing but K times the tension, K times the deformation of the spring. So okay, with that, we still have this ask where we're asked to figure out what is the original undeformed length of the spring. It would be so legit for anybody to look at this and say, I don't even know where to start. On the other hand, let's always remember, when we're uncertain, let's draw a free body diagram. Okay, free body diagrams are everything. So in this case here, let's kick this whole thing off by drawing a free body diagram of our plate. If we do that, we're going to draw the plate itself exactly as we're representing here. We know there's a pinhole in the plate, maybe roughly right about there. We got a pinhole in that plate. Now, let's do the same old, nothing's new here. So, free body diagram, sketch, coordinate axis system. The standard one's going to do just fine. We have already been told that this plate is uniform and it has a weight of 196.2. So right in the geometric center, we're going to show a weight going straight down, and we know that that weight is 196.2 newtons. We also have a pinhole here, and we have already asserted that the pin, because it's ideal, is frictionless, it's smooth, and we have seen now many times for pins that we just represent pin forces as some arbitrary X force and some arbitrary Y force. Now before we do that though, ask yourself, could this possibly be a 2-force member? The answer should instantly be no. Why? Because there's a bunch of criteria that doesn't get met. Number one, 2-force members have to have 2 pinholes. That one's got a grand total of 1. So nope, you're out. 2-force members have no weight. This thing does have a weight. So we can't make any simplifications on that. We kind of check the box, not a 2-force member, go on from there. So therefore, up here, I do have some arbitrary X force. I got some arbitrary Y force. I don't really know the directionality of these things. It doesn't matter. So OY, OX, I'm good. Doing fine with that so far. And again, folks, remember, it's a pin. The standard representation is an X force and a Y force. If you ever forget that, you can always ask yourself, hey, if the pin was still there, can I move it in the X direction? Nope, X force. Can I move it in the Y direction? Nope, Y force. Remember that. And then lastly, folks, is that spring sitting over there. Now remember, when it comes to the spring, we kind of breezed through this when we went through the different representations. Spring forces kind of look like tension member forces. If you look at the axis of the spring, it's merely an axial force on that, that same axis. So what I'm going to represent for right here, the spring, which again, in fairness, that is a point where it used to be in contact with something. So right here, I'm going to show a force for the spring. In this case here, that's a compression spring, meaning it takes force to push down. The spring is pushing back and applying force on this. So it would be legit to think that the force of the spring is going up that way. So now, let's pause for a second here because I want to make sure everybody in the room is completely comfortable with the fact that that's a complete free body diagram. We have the sketch of our part. We got our coordinate axis system. We got the weight, which we were told. We've got the force where I used to be in contact with something right here, the spring force. We got the force where I used to be in contact with the pin right there. Free body diagram. It's done. Yes?
Is there a normal force for the spring?
There's not. Good question though. Fantastic question. And there's two reasons for it. Number one is, again, springs we treat just like tension, like there's a rope there, but there's not a rope there. But we treat those as singular forces right on their axis. So that's one reason not to. The other reason is, again, we assume that all surfaces are smooth. So in this case here, if the spring was actually on this smooth surface and there's no friction here, there wouldn't be any force that way. So it's a great question. Any other about the free body before we move past it? All right, cool. So now, this is an important idea. Folks, I want you to look at this. Right now, I got one free body diagram and I got a grand total of 1, 2, 3 unknowns. We all know that with a free body diagram, as long as the forces aren't concurrent, meaning they don't all intersect at some singular point, which these do not, we know that with any free body diagram, we got a budget of 3 equations of equilibrium. We can sum forces in x, we can sum forces in y, and we generally will sum moments about some other point. Meaning, with 3 unknowns here, I can solve for each and every one of those unknown forces. Here's the question for you though. Do you need to? I mean, the question's asking us to figure out the deformation of the spring, right? Based on that, do we have any reason to think that we need to know what OX is or what OY is? And again, there's no wrong answer here, but the voice of common sense might say to you, well, I probably don't need to know what that is if all I care about is what's the force in the spring, because if I know the force in the spring, think about this. If I know the force in the spring, and I know that that force is equal to K deformation, and I know what K is, then I got visibility in my deformation, right? So this leads us to a whole new branch of decision making that we can do whenever we're making a problem like that or doing a problem like this, and that is, if the problem doesn't specifically say, hey, tell me all these forces, which this one doesn't, you don't have to find all the forces. Meaning that even though you could write 3 equations of equilibrium and figure out each and every one of these things, the question becomes, and this is important for today, it's important for our future, the question becomes, could I write 1 equation of equilibrium and get the thing that I want? What do you think? Could we write 1 equation of equilibrium and figure out what Fs is? Oh, somebody throw a dart at, take a stab. The answer is yes, by the way. What would happen if we wrote 1 moment equation about point O? If I wrote 1 moment equation about point O, then OY is not going to be in that equation, OX is not going to be in that equation, this will be in the equation, this will be in the equation, and nothing more. 1 equation means I get the solution that I want. So while we could sum forces in the x direction, we could sum forces in the y direction, and we can take a moment equation. It turns out that if we're choosy about where we take the moment equation, then we get what we want. We don't have to worry about summing forces in x and y. And we're going to see this many times as we go forward, folks. The idea that you want to learn how to become judicious about where you put your moment equations, because it just makes the math overall much, much easier. So with that, let's do that. Let's do that right over here on the right-hand side. Let's sum moments here about point O. Let's do what we always do. Let's draw the counterclockwise is positive symbology in there, folks. That just reminds us of our convention here. So I'm going to sum my moments about point O. What do I have? I'm going to start things off with my 196.2. So again, point O here's my moment center. I look at the 196.2, it's pointing down here, folks. I know I can slide it anywhere I want along its line of action. The way that's pointing down like that means that if I constrain it here and let it rotate, that's causing a clockwise rotation about that point right there, which means that's a negative moment. So I'm going to have minus, because of the clockwise rotation, I'm going to have minus times the magnitude of the force, so 196.2 newtons times my moment arm. So my moment arm, folks, we'll all remember, is simply the distance from my moment center to the line of action of the force, and the line of action goes forever, that distance making the 90-degree angle. So I need to know the distance from here over to here. If I go back to my original diagram, you've got to kind of synthesize this one a little bit. We see that the overall width of the plate here is 0.12 plus another 0.48. So that means, adding those two together, 0.6 meters here, which means that the halfway point would be 0.3. So if this is 0.6 and the halfway point is 0.3 from this edge, but point O is already offset in 0.12. So that means the distance from here over to the center of this is 0.3 minus the 0.12, or 0.18. So again, if it helps you, you can do this. So this distance right here is 0.18 meters, right from there to there. So I'm going to come over here now to my equation. And I'm going to add my moment arm here of 0.18 meters. And that takes care of the moment due to this force. Now again, let's just reiterate, let's hammer this point home. OX is not in the picture, OY is not in the picture, because their lines of actions pass right through the moment center. But I got FS over here. Now FS, the way that it's drawn, that's going to be causing a counterclockwise rotation, so that one's going to be positive. So back over here to our equation, we'll have plus Fs, and then I need the moment arm for that one. So in this case here, I need to know the distance from here over to the line of action of Fs. Remember, the line of action goes on forever. So I need to know the distance from here to here. How do I get that? Well, several ways, of course. Keep in mind, the distance from here, according to our original, the distance from here over to here was 0.48, but this force comes back in 0.15. So if I go 0.48 and then subtract 0.15 from that, I'm left with 0.33, if I'm doing my mental math right. So that distance, therefore, should be 0.33. Now over to here. And in our moment equation, those are the only two forces that are going to be in the moment equation. Again, just to beat the dead horse here, we took care of that force, we took care of that force, and we said these two are not in the picture. So we've taken care of everything. So let's set this equal to 0. And now, ladies and gentlemen, with that set equal to 0, we step back and we look at that moment equation and we realize we're going to get solved that equation, or I'm sorry, we're going to get solved for Fs just from that equation alone. We didn't need any other equations to do the job on this one. If we do this and we solve for Fs, we're going to find out that Fs ends up being, and of course I'm not going to write it all down here, folks, but this whole term here is going to become positive on the other side of the equal sign. We're going to move that over there, divide by 0.33. And when we do that, folks, we're going to find out that Fs is equal to 107 newtons. Now, as I said, this problem's got a lot of issues with it, a lot of quirks. The first thing I want you to notice here, ladies and gentlemen, is our units for force here are in newtons. But when we go back and we look at our modulus, the value for the modulus was given to us in kilonewtons per meter. So newtons, kilonewtons, we got to get these things to line up, right? A couple of different ways we could go about it. We could convert this over to K is equal to 2,000 newtons per meter. That gets the job done, easy peasy. Or we could convert this over to kilonewtons. Either way goes fine. In this case here, let's convert to kilonewtons. Let's just turn this over, and 107 newtons, we have to divide by 1,000 to turn it into kilonewtons. So this is the same then as 0.107 kilonewtons. So now with that, folks, we see that we know what Fs is. And I want to pause here before we go any further with this. Before we did our free body diagram, before we just did the stuff that we always do, we were tasked with a question of figuring out the undeformed length of this thing. And again, as I said, it would have been very legit if anybody would have looked at that and said, I don't even know where to start. But now look where we're at because of what we did by just following our own rules of let's just work the problem, let's figure out some forces here, use free body diagrams and all that. Right now, we know that Fs is equal to 0.107. If I come back over here and I use this equation here, that means if Fs is equal to, again, K delta, that means that delta, the deformation, is equal to, therefore, Fs divided by K. And that's going to be equal to, we just figured out Fs over there is 0.107, so 0.107 kilonewtons divided by the K value, which was 2 kilonewtons per meter. And folks, those kilonewtons are going to cancel right out. The 1 over meter is going to become, flip it up to the top, it's going to become meter. So 0.107 divided by 2 ends up being right around 0.54 meters. So, actually I think I may have, yeah, I'm sorry, I wrote that down wrong. It is not 0.54, folks, it's 0.054. 0.054 meters. So now the question becomes, what does that mean? Is that the answer to the problem? Well, it turns out that's not the answer to the problem. That's actually how much did I need to deform this, how much did I need to squeeze this down to get it to fit into here. But when I squeezed it down, this amount of deformation, I had 0.1 meters left over, right? Which means my original deformation had to be the 0.1, or I'm sorry, I said original deformation, I meant original length of the spring, had to be the 0.1 plus the amount of deformation. So therefore, the final answer on this is that L is going to be equal then to 0.1, the deformed length, plus the deformation delta, or 0.154 meters. And that, folks, solved the problem. The most important takeaway here that I want you all to have is not that this problem was a bunch of weirdness. It was that to get past the weirdness, we just did the same old. Free body diagram, equations of equilibrium, which in this case, one equation of equilibrium, that's all it took. And all of a sudden, we're in business. Question?
For the equation for the force of the spring,
Yes.
couldn't you also write it as the change in length instead of the single s?
Yeah, you could. I want to make sure I got that part. Are you talking about this thing right here?
Yeah.
Yeah. Even though that looks like an S, it's actually meant to be the Greek symbol lowercase delta. All right, so we commonly use delta to mean a change in length. So, yeah, it's a great question. Any other questions you guys might have on that particular one right there? All right, let's get this one cleaned up and move on to the next. Like I said, we got 4. These next 2 will go a little bit quicker here, folks, I believe. Now, pre-warn you on this next one I'm about to draw, I'm going to pause a minute here. I'm going to have you draw in your notes what you think the free body diagram should look like, and then we'll come back and take another look at it.
I don't know how people see me.
Okay, folks, I think I've got everything up there that we're gonna need to, in order to be able to process the narrative on this one, but let me read through the narrative, in detail with you, and then, like I said, I'd like you to just take a minute and kind of think through, well, if you were doing this free body diagram, how would you do it? So, here's what the narrative says. When the 0.05 kilogram body, and by that they're referring to this T-shaped bracket right here, so we're being told that this is a 0.05 kilogram body, is in the position shown, the linear spring is stretched 10 millimeters. The question we're being asked to do here, folks, is determine the force P. So we have force P right here. Determine the force P required to break contact at point C. And then we're going to do this two different ways. I'll come back to that in a moment. I don't want to go into the ask here, but I want to stop right here and just simply say, I've got a 0.05 kilogram body right here. By the way, we're not told anything about it being uniform, so in this case here, we have to make the assumption that it is. And if you look at this, we do have a line of symmetry right here, the pinhole notwithstanding, so you can treat this as though your line of symmetry is going right down the middle of this vertical piece right here. So the 0.05 kilogram body, linear spring, determine the force P required to break contact at C. We're going to do a free body diagram of this bracket right here. Take a moment, just kind of sketch out what you think that should look like. Take another few seconds to give everybody a chance to kind of think through this. How would you do this one here? Okay, folks, let's work through this one together then. So now, we already know that this thing has a certain amount of weight. The weight here is going to be the mass times gravitational constant. So weight in this case would be 0.05 kilograms times 9.81 meters per second squared. We plug that in and crank that out, folks. We're going to get a weight here of 0.491 newtons. So over here on our free body diagram, since we asserted that we've got symmetry right down the middle of this this leg right here, the weight can be shown anywhere on this line of symmetry. So maybe I'll bring it right down here, and I'm going to show my weight right there as the calculated 0.491 newtons. And again, remember, that vector can slide anywhere we want it to be. It doesn't matter that I put it down here. It could be up here. It makes not one iota of difference. What does matter, though, is I put it on this symmetry line, and I'm pointing straight to the center of the Earth. All right, so that part I'm following. Now, I have a pinhole here at point O. The narrative of the problem was silent on whether or not the pin was, I don't think it called it ideal or anything, but remember, unless we're told anything's rough, which we won't be till chapter 6 for anything we're doing from this point forward, we assume it's smooth. So, okay, got a smooth pin up here, so maybe I've got some X directional force here, I'm going to call it OX. Maybe I got some Y directional force right here, I'll call it OY. Again, folks, I hope you're all getting to this point here. When you see a pin, just right off the bat, you just think, hey, X force, Y force. It's really that simple, unless, again, you see a 2-force member. But as we talked about in the previous one, 2-force members can't have any weight, so it's automatically out. This is not a 2-force member. Now, we also know that we've got this force P applied over here, and we're going to be finding out what that P is in just a quick moment. And then very, very importantly here, folks, very importantly, we've got the spring force, all right? The spring is pulling on the bracket off like this, and the force of that spring is going to be the modulus of the spring, which is written up here at K as 1,750 newtons per meter. We were told that we were deformed, what did they tell us here? We were deformed, 10 millimeters. So the deformation is actually 0.01 meters. So the force on this spring here, let's just write this up over here. So force of the spring is going to be equal then to K delta, which is going to be then 1750 newtons per meter times the deformation, which we were told was 10 millimeters, but that's the same as 0.01 meters. So we got to make our units match. So 0.01 meters, and folks, plug that in, crank that out, you're going to get 17.5 newtons. So the force on the spring is going to be 17.5 newtons. Now, I'm pausing here, I'm stopping right here, because I mentioned to you in the previous that the authors kind of lied to you a little bit here. And this is just an FYI, this will become more important to you in later courses like machine design. The force of the spring, K delta, that is correct whenever we're dealing with a compression spring. It's not correct for a tension spring. See, tension springs actually need an initial amount of force to get them to start deforming. It takes an amount of force to start the deformation, then after that, it's K delta. So the true equation for an extension spring is K delta plus Fi, or force initial. The authors ignored that in this case here. They just figured you don't need to know that for now, I guess. But if somebody has already worked with springs, you might be looking at that thinking, wait a minute, I'm missing something here. Yeah, you would be right in that case, but they don't go down that path. So okay, whatever, 17.5. So over here, we know that this force is 17.5 newtons. So again, let's think about this. Applied force, weight, spring force, OX, OY, the pin force. Folks, if the free body diagram that you wrote on your paper looks like that and stops right there, your free body diagram is correct. On the other hand, it would not have been a surprise at all if your free body diagram would have contemplated that you were in contact here with point C. So since you were in contact, shouldn't there be a force there? Oh, but no. Remember, we saw this just the last time we got together, where every now and then the author's going to slip in some language that tells us that there is no contact. Look at this one here. This one's actually a little bit more overt. It says, determine the force P required to break contact at C. So they were literally telling us we need to know the force it's going to take to let there be no contact there. And if there's no contact, there can't be any force. So because of that, if your free body included a force here at C, any representation of a force here at C, that would have been incorrect because there is no contact there. The impending motion has already taken place. We have no contact, meaning that right there, folks, is the complete free body diagram. Now, with that free body diagram, and let me pause on that. Does anybody have any questions about the free body diagram here? Good. Now, with that, let's go back to the ask. This problem asks us to do the following. It says, complete the solutions for A, including the effect of the weight, and then B, neglecting the effect of the weight. In other words, the ask here is, how much force P would have to be pressed down here to cause contact to break on C? The first pass, we're going to include the weight. The second pass, we're going to not include the weight. And in this case here, again, it's not at all a bad idea. In fact, it's a great idea to kind of ask yourself, well, what do you expect the outcome is going to be? And the takeaway here would be this. If I'm including the weight of the bracket, which is inherently pushing down here and trying to make the bracket swing away from this point C, then if I'm including the weight, it should take less force here to break contact with this. But if the weight is no longer a factor, it's no longer assisting me, then it's going to take more force without the weight. So my outcome of my equation, my math here, tells me I should think that I'm going to see a little bit more force on P when I exclude the weight. Now, in the same vein of the previous problem, if I look at my free body diagram, I have a grand total here of 1, 2, 3 unknowns. That's a known force, that's a known force. 3 unknowns, 3 equations in the budget, but I only need 1. It's the same thing we talked about before, folks. I can figure out what OX and OY are, but I'm not asked to. I don't care. So in this case here, all I want to know is P. So if all I want to know is force P, then I can write one equation, one moment equation, through point O, which will take OX and OY out of that equation. The only unknown I'll have is force P, and I solve the problem. So let's do that. Let's sum moments. Let's sum moments about point O. And let's see what we got here. First off, I'm going to take care of force P. Force P is causing a huge counterclockwise rotation about point O, so therefore it's positive. So I'm going to have P times my moment arm here, which from these original dimensions, all dimensions were in millimeters, so from here to here, grand total of 120, so P times 120 millimeters. Now, let's take the 491, the 0.491, that too is also causing a counterclockwise rotation about point O, so it's going to be positive, so plus 0.491 times its moment arm, which, folks, from here over to the midplane is simply 60. Done. And then I've got this force due to my spring here. Now, if I look again, my moment center's up here at point O. The force of the spring's pointing to the left. If I imagine that's anchored and tied and then let it fly around, that's going to cause a clockwise rotation. That means it's negative. So minus 17.5 times its moment arm, which is merely the distance from point O down to the line of my spring here. So that's going to be 40. And folks, I've taken care of now all the forces. Again, OX, OY, they're not in the picture. I took care of the moment due to P. I took care of the moment due to the spring. I took care of the moment due to the weight. There's my equation. Yes, fire away.
Should the distance be changed to meters?
Yeah, that's a great question. The answer is it doesn't matter, because what's going to happen, they're all going to cancel out. Yeah, so it's one of those questions that if we're being super purist, yeah, but since it's going to go away, it doesn't matter. But with this now, I can solve for P. In fact, in this case here, folks, if I look at this, P is then going to be equal to, as these things slide over the other side equals, so I'm going to have 17.5 times 40 minus 0.491 times 60 divided by this 120 right here. And by the way, that right there is why they're all going to cancel out. We can see that those terms are just going to go away. And folks, if I plug that in and I crank that out, I'm going to find out that my force required to break contact here, this works out so that P is going to be equal to 5.59 newtons. And if you remember, our narrative, or our ask in the problem was to solve it where we include the weight, but then solve it again where we neglect the weight. So in this case here, to neglect the weight, this is really easy. All we need to do is just make the weight term here go away. So if I set that weight to 0 and resolve the problem, in this case, I would get a new value of P, which is going to be 17.5 times 40 divided by 120. That one works out to be 5.83 newtons. And that's very quickly solved. And it's worth noting, folks, it came out with exactly what we expected before we started the problem. We said that we thought without the weight that it was going to take a little bit more force because we don't have the weight helping us anymore, and that's exactly what we came out with there. Now, it wasn't a ton difference, but there was some difference on that, and that solves that problem as well. Once again, we get to see that regardless of the ask doesn't really matter. The pathway to get there is just a free body diagram and work the forces. Questions on that one? Anybody? We got one to go. Okay, let me clean this up. Remember now, we're going to be ending chapter 3 with this one here, folks. It's just a bunch of examples of basic equilibrium problems. Again, The common denominator is it all happens with a good free body diagram. Doesn't matter what everything looks like, it boils down to a free body diagram. We're going to finish chapter 3 here when we get together again on Monday. We're going to be into chapter 4, and that's where we're essentially, as we get in chapter 4, we're basically where we, well, let's put it this way, the can crusher problem that I started at the beginning of the course was in chapter 4, so we're kind of there. All right, on a second here for me to find this. This one takes a little bit of artwork, so bear with me on this one here, folks. Folks, as you can see from the diagram up here, this one's got some stuff going on. Even then, I'm not quite done. So we gotta. All right. There appears to be a lot going on with this thing here. Let me read the narrative. This one here will by far be one of the longest narratives we've seen so far. It goes like this: a portion of the shifter mechanism for a manual car transmission. So we're talking about the shifter on the floor of a car that's got a manual transmission on that. Portion of the shifter mechanism for a manual car transmission is shown in the figure. For the 8 Newton force exerted on the shift knob. Folks, what I want to note here is 8 newtons is being exerted on the shift knob. Somebody's grabbing it, trying to move it forward with 8 newtons, and we're showing that that is on a 5-degree offset from horizontal. So for the 8 Newton force exerted on the shift knob, we're asked to determine the corresponding force P exerted by the shift link BC on the transmission, and the transmission is not shown. What we're saying here is grab the knob here, apply 8 newtons here. This is going to try to move forward. We got a pivot mechanism here. Rod BC going through what I'll talk about here is applying a certain amount of force P on the transmission, which is down here. We're not showing it. We only care about what that force P is right there. Now, we're told several things. Neglect friction in the ball and socket joint at O. In other words, actually no, if I call this a C. This is actually a point O right here, folks. So what I wrote as C is really point O. So all they're saying is in this ball and socket joint, which is this thing right here, which we have never seen a ball and socket joint before, right? But the ball and socket joint, there's no friction in that surface right there. And also in the joint at B, so there's no friction up here at B. And in the slip tube near support D. So down here there's this slip tube going through this bearing surface. There's no friction down here either. It is, oh, and then one last thing. Note that a soft rubber bushing at D allows the slip tube to self-align with link BC. And that's what's being shown right here, folks. There's kind of a soft surface in there, which lets that, accounts for a little bit of motion in this as we operate at slightly different angles. That right there, folks, is not important information. It's just that it was thrown into the narrative. But what is important in that, folks, is the narrative comes out and tells us that we can neglect friction here, here, and in the slip joint down here. What it doesn't say is neglecting friction anywhere else, but it also doesn't say anything about it being rough anywhere else. So that just simply means that even despite it saying all that, neglect friction here, there, and everywhere else, there is no friction anywhere. So we just neglect friction everywhere. Fine. So now, the ask that's in front of us is to figure out if the person using this applies 8 newtons of force to the shift rod up there. What is the force I'm going to get here at P pressing on the transmission? And this goes back to, again, hear these words. There is nothing new here, folks. This is the same old, same old. All we need to do is decide, well, fine, what do we want to make a free body diagram out of, and let's go from there. All right, now, we have looked at a number of different problems. Even today, we looked at one where the free body diagram was nothing more than the knot in the rope. but I've said it before, we can pick anything we want for a free body diagram, which includes combinations of things. In this case here, what would happen if we did a free body diagram of this entire shaft here plus this piece right here? So I got the entire shifter rod plus this piece. Let's do that one and let's see what it's going to do for us. So I'm going to isolate that part, or actually in this case combination of parts. So I've got my shift knob head here, I've got this coming down over like so, coming down over like so, doing a little bit better than that. I've got this piece here, and I've got a portion of that piece coming down, which we don't really see it. There's a pinhole back here. And the rest is coming down, and now here's the ball from the ball socket there. So I have done a free body diagram right now of just sketch so far of the shifter arm and this piece connected to it, where I used to be in contact with that pin right there, and I used to be in contact with rod BC right there. Okay, now with that, let's complete our free body diagram. So we've made our sketch, everything's isolated, there's no ghost lines touching or anything like that. I'm going to use a standard X and Y coordinate axis system on this one, folks. Let's start with, were we told anything at all about the weight of the shifter arm? No. Therefore, we don't need to worry about its weight. We do have an applied force up here of 8 kilonewtons. So, or I'm sorry, 8 newtons, not kilonewtons, 8 newtons. Same 5-degree angle right here. Got that. So that's applied. Again, no weight. Now, I want to focus on that right there. That is a pinhole. It would not be wrong to think that, well, okay, pin, X force, Y force. Not wrong. But on the other hand, we actually know more than that. If you think about this, folks, we were told there's no friction here, right? Matter of fact, the authors went to great lengths to tell us there's no friction here, which means I've got a rod here, which I have a known force P on that rod. If I have a known force P on this rod, then the force back up here where that rod connects to that must be the same force P. It's got to be. But what's important here is to realize that if force P on this rod is shown going that way over here, then it must be shown as equal and opposite over here. If it's not shown as equal and opposite, the problem will not come out right. So I'm going to show the force P right there with the same 15-degree declination angle here as that, and that's the only force I've got on that pin. It's the only force I can have on that pin. So now, with that, I've got the force here, where I used to be in contact with something. I used to also be in contact with the ball, the socket for the ball down here, but we haven't seen one of those yet, right? We have not seen one of those. Here's where that ability to say, okay, when I don't know, I can trust the idea that I can ask myself, could I translate this in the X direction, and would I face resistance to motion? So if this thing here really was embedded in that socket joint right there, and I try to move this thing here in the X direction, would I face resistance to motion? Sure. So I'd have an X force. So how about OX? If I tried to move this down, up or down in the Y direction, would I face resistance to motion? Sure. So therefore there's going to be an OY. Do I know those directions? Nope. Do I care? Nope. Right? Now, if we were not told that this is a smooth surface, then it would also be reasonable to think that you'd have some sort of a moment in there. But because that surface is smooth, there's no resistance to rotation. Therefore, we don't show a moment here at all. And now, folks, if you take a look at that, you'll realize that's a complete free body diagram. So now, what went from looking pretty messy over there has went to one free body diagram with, in this case, 1, 2, 3 unknowns, but following the theme of the past two problems, we don't even need to do anything more than one moment equation about point O right here, because I don't care what OY is, I don't care what OX is, I was asked to figure out what P is, and one equation is going to get me there. So that one equation well, I think before we do that, let's do the following. Let's resolve our forces. Because here's where we gotta use Varignon's theorem. If we're writing a moment equation, we gotta use Varignon's theorem. So if I resolve this force here, this 8 Newton force, into its x component and its y component, first of all, tending positive x, tending negative y, I can slide it and anchor it right here because I know where dimensions are right here. So I'm gonna have a force going down like that, a force going over like that. This one here is gonna be 8 times the cosine of 5. This one here is gonna be 8 times the sine of 5. And I know I'm going fast through that, but we've seen this now plenty of times. So once I resolve the force, I get rid of the original force. I no longer need it. I'm going to do the exact same thing here. I'm going to slide this force over and anchor it right here because I know that's where I've got dimensions. So in this case, I'm going to have a tending negative x, tending positive y. So this one here is going to be p times the cosine of 15. This one will be p times the sine of 15. And with that, I get to get rid of now the original force. I don't need it anymore. So now my free body diagram is looking like that. But now that puts me in position to write the moment equation because I'm using Varignon's theorem to make my moments a lot easier. So now if I sum my moments about point O, let's see what we have here, folks. Let's start with the p cosine 15. Again, our moment center is right here, so OX and OY, they're not in the picture. P cosine 15, that is doing it counterclockwise, so it's going to be positive. So P cos 15 times its moment arm, which is going to be the distance from point O up to this line right here, which is moment arm of 75. Let's now do P sine 15. So look, this is offset to the right of this here. It's a little bit easier to see here. This is offset to the right, and we know that P sine 15 is pointing upwards. So therefore, if it was over here and pointing upwards, that would also be causing a counterclockwise rotation. So that's going to be positive. So it's going to be plus P sine 15 times its moment arm, which is merely going to be this little distance from here to here, which we see that in this dimension right here, which is 25. Now, let's take care of the 8 cosine 5 way up here. With the moment arm down here, that is causing a very large clockwise rotation, so that's going to make it negative. So minus 8 cosine 5. And the moment arm on this one, okay, that's going to be, so it's way up here. It's going to be 75 plus 188, which, what is that, about 263, I think? Yeah, about 263. Actually, I wrote it written down. I should be able to see it. So 263 right there. Now lastly, we see that we've got this y component here, which we said was 8 sine 5. But that's going to actually come way down here and pass on the left-hand side of O. Its line of action goes forever, as we know. Passing on the left side of O, which means if it's passing down here, that's causing a clockwise rotation, or counterclockwise rotation, so that one's going to be positive. So plus 8 sine 5 times its moment arm, which in this case, here's the center again. From here over to here, we see 25 on that one. And folks, if you step back and do this every time you write a moment equation, always step back and ask yourself, did you get all of the forces? And yes, the only two forces that are not in the equation here again are OX and OY. There are 4 forces in this. They're all showing up in our equation. We set this now equal to 0. And folks, if you look at the equation in front of us, there's only one unknown in that equation, and that's the thing we're looking for, and that's force P. So in this case here, we can solve for P, folks. It's going to go something like, let's see here. I can combine some stuff here. So I'm going to have P times all this stuff here. So 75 cos 15 plus 25 sine 15. That's going to be equal to, when I move this to the other side, the equal sign becomes positive. This would become negative. So do all that. That's going to work out to be 2078.6 The units on this, by the way, folks, just we're wondering, it's Newton millimeters. And this is gonna be in newtons. So now I'm gonna solve for P. Obviously, all I gotta do is just divide by this term here on both sides. And folks, when all is said and done, we get 26.3 newtons. I didn't do it again before the start of this problem. Probably should have, but it's another one of those, kind of ask yourself, what do you expect for this? If you think about this, if I'm applying 8 newtons on the shift arm here, I certainly would expect that that's gonna amplify somewhat. So does it amplify, 3, 4, 5 times? In this case here, it looks like somewhere between 3 and 4. That's a very legitimate outcome. So that would be within expectations. But there you have it. What's the takeaway on this, folks? One last final time. The takeaway is we went from a problem that at first looked really busy, had a lot of narrative. We waded through all the BS in the narrative, and what did we come up with? One free body diagram. And when we had the one free body diagram, we applied one equation of equilibrium, and we solved that problem. That is basic equilibrium, folks. Questions on that? We've seen 4 problems today. 4 problems today. I'm going to come to you in 2 seconds here. We've seen 4 problems today, and every one of those problems, regardless of what the ask was, we just did free body diagrams. We made sure those free body diagrams were right. Then after that was just equations of equilibrium. Yeah, far away.
How did you get 2,278?
I got it by this term right here, multiplying that together, and then subtracting from it this amount right here. Did you get something different when you calculated it?
788.
How many?
788.
I don't know. I've done this one for years and years, and I've always came up with the same, but I can look at it again.
I might be, I'm in radians, that's probably.
Oh yeah, that fixes it. Thank you. That had me worried. Yes, way back there.
What happened to the negative?
Which one?
On negative 8 cosine of 5 times 263.
Yeah, great question. So what I did was I combined these two into this term right here, but then I moved everything else over to the other side of the equal sign. So when I moved this one over to the other side of the equal sign, it became positive. This one became negative, and I just did the math and came up with that 2,000 plus.
Yep.
Good. What other questions you guys got? All right, go have a great weekend. See you all on Monday. We're in chapter 4 at that point.